All right, welcome back, everyone. We're going to continue this week's lessons on circuits by focusing on the second type, parallel circuits. So, different from yesterday's series circuit where there was only one path, parallel circuits have more than one path to travel. And the cool thing about these circuits is that if one part fails, the rest of the circuit should still function just fine. And so, if you recall yesterday's example of Christmas lights on the movie Christmas Vacation, where they weren't lighting up, and so he sent his son to check every single bulb. You wouldn't need to do that nowadays because Christmas lights are sold in strings that are wired in parallel. So if one part fails, usually it's just that one bulb or just a short chunk of bulbs that you would need to deal with and try to figure out how to fix. And that's easily done. I know that because even I can fix it, and so that's good. The resistance of a parallel circuit is a little bit more complicated to find. It's using an equation that deals with reciprocals. In a sentence, it says resistance in the entire circuit is found by adding up the reciprocals of each resistor, and then the total is the the total in the circuit is the reciprocal of that answer. It's just even hard to read. This is what it looks like. So when I use this equation, I like to take care of the denominator first. I figure out the reciprocal of the first resistor and I add it to the second and to the third, etc. And then I take the overall reciprocal of that answer. So it's multiple steps just to kind of make sure you're not screwing it up on your calculator. And the more resistors you have, the more annoying this is, but it's not that bad. So I'll show you how it works. So let's say this is our parallel circuit. Notice the picture is a lot different. We've got multiple paths for the electrons to flow through. And so let's say resistor 3 has an issue, it malfunctions. The other two should work just fine and have current flowing through them. Let's say I gave you these values. Resistor 1, 8 ohms, resistor 2, another 8 ohms, and then resistor 3, 4 ohms. What is the total resistance, first of all, in this circuit? Well, we're going to use this equation here. It's just what you saw on the previous slide. And we're going to plug in our values, our three resistors. I like to break it down into a couple steps. First, I find out the decimal answers of each reciprocal. So 1/8 plus another eighth plus a fourth. I sum those together to find that it's 0.5, and then I take that reciprocal at the end. 1 divided by 0.5 gives me an overall resistance of 2 ohms. Now I want you to pause for a second and realize how weird that is. The total resistance of this whole circuit, 2 ohms, is much less than any individual resistor within the circuit itself. And that's the odd thing about parallel circuits that you have to kind of choke down, that the more resistance you add, the overall resistance decreases. So if I were to add a bunch of resistors, you'd see this number go down, 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 down. And I'll show you that later. And the reason being it's because of this equation, okay? So if you have less resistance overall, we should see an increase in current, and that's what we'll see here. So what is the total current through the entire circuit if, let's say, there's a 10-volt battery? Well, we can calculate that by using Ohm's law. I is equal to voltage divided by resistance. So we're going to use our 10 volts here in the problem, divided by the total resistance of 2 ohms, gives us 5 amps. Now 5 amps is a lot more than any example we covered yesterday. Typical amps running through those series circuits was like a half an amp or 1.5 amps, a lot less than 5 amps. So I want you to note that parallel circuits, because of this whole decrease in resistance, have a lot more current than series. Let's talk about voltage and current in parallel circuits. Yesterday, as we covered series circuit, we learned that the current remains constant because there's really only one path or one flow to measure. With a parallel circuit, it's the voltage that remains constant at all locations. The current is going to vary in each loop or each branch, and you can calculate each current in those loops by using Ohm's law. And you can check your work because if you add up those currents, it should equal the original total current that we calculated to begin with. One thing to note in a parallel circuit is that the more resistors you add, the more current you're going to draw, and this can be a bad thing because it can lead to an overload of the circuit. You're never going to have that problem with series. because as you added a bunch of bulbs, it got dimmer and dimmer. You're not going to overload in that regard, but adding in parallel, I'll show you how that can be a problem. So let's continue with this example. This is the same picture you saw before. Just to remind you, what are each resistor equal to? 8, 8, and 4. We found that the total resistance using that ugly equation was 2 ohms. We said that we're going to use a 10-volt battery, and we calculated total current by taking 10 volts divided by 2, sorry, this should be 2 ohms. Let me fix that here. So 10 volts divided by 2 ohms gives us our 5 amps. We can calculate the current at each branch, so this current, and this current, by using Ohm's law. So the first branch here, we're going to use I equals V over R, but because voltage remains constant no matter where you are in the parallel circuit, we're always just going to use 10 volts. The resistors, however, are going to be different at each spot. So 10 volts divided by the 8 ohms right here, I know that because that's the information I gave at the beginning, gives us 1.25 amps flowing through the first branch. The second branch is going to be identical because the resistor is the same. 10 volts divided by 8 ohms gives us another 1.25 amps. The third branch, you're going to use 10 volts and divide by 4 ohms to get 2.5 amps. So notice there's more current flowing through the one with less resistance, which makes sense. Now, to make sure you did it right, you just add up those three together, 1.25 plus 1.25 plus 2.5, and that gives us 5 amps. And I know that's right because I calculated that to be my total current to begin with, okay? So in a parallel circuit, the current splits among the branches, and it's pretty easy to calculate how much it splits by using Ohm's law here. I want to also show you another way that you can draw parallel circuits. Notice there's multiple branches here. If this one has an issue here, this 8 ohm, let's call it a bulb, the others are just going to be fine. They'll still light up. Now, one thing I should mention about that though is that there are certain key points in a circuit, like let's say this wire right here corroded. That's going to be bad because now the electrons don't have a method to get to any of these branches. So if you have an issue in this spot right here, yeah, the whole thing's not going to work. But what we say about, the whole circuit still functioning, that's just if we have a problem with any of these individual resistors, okay? So what happens if we add a bunch of resistors? You'll notice there's a lot more branches in this problem. All I've done is I've added 2 additional resistors of 4 ohms each. Adding resistors is actually going to decrease the total resistance in a parallel circuit. This is the exact opposite of what you'll find in a series. And the reason being, again, we're going to have to go back to this equation. I do have you do this equation in a quiz, so I want you to be comfortable to know the steps. Definitely have it in your notes. And so let's look at it. So 1/8 on the bottom plus another eighth plus a fourth, another fourth, and yet another fourth. If you actually sum these fractions together, you'll get a 1 at the bottom. So the reciprocal of 1 is easy, 1 ohms. So the total resistance decreased as a result of adding more resistors. Again, weird, counterintuitive, but it's due to this equation. So if we have less resistance, we should see a rise in current. I equals V over R, and we're going to use our 10 volts in the picture divided by our overall total resistance now, and we should see 10 amps flowing through this overall circuit. Now the 10 amps is going to split among these branches, but if you summed these together, you would get the 10 amps flowing through the whole thing. That's a lot more. In fact, it doubled compared to our previous example. So the thing I want you to take away from this is that adding resistors in parallel increases the current. And what that means in a practical sense is that if these were bulbs, you would see them getting brighter and brighter and brighter the more bulbs you add in parallel. And eventually, if you add enough, you'll probably overload the circuit and they'll just burn out. So I like to kind of compare them side by side. The top here being series. I use different symbols now for, this is specifically for light bulbs. You should have covered that in a couple days ago when you looked at circuit schematics and how to draw these. Notice when I have them connected in series, they start out pretty bright, but if I add additional bulbs, they become dimmer. And that's because adding resistors in series increases the total resistance. Again, you just add them up. And that's going to decrease the drawn current. Now, one good thing about that is that the battery will last longer, but the cons are that, okay, if one part fails, the whole thing fails. And the other con is that, the bulbs get so dim they're practically useless. In a parallel, however, here's again how to draw, one way you can draw a parallel circuit. As we have three in parallel, excuse me, I can't even talk, parallel, and we add a couple more, notice how much brighter they get. Adding resistors decreases total resistance, and that's going to increase the drawn current. And so they'll become nice and bright. However, the con is that not only are you running the risk of possibly overloading the system, but your battery is going to drain so fast. And so very different situations here. To put them in a list side by side, I encourage you to have these differences down in your notes, because tomorrow you're going to take a quiz that really tests if you understand what the differences are here. So I put them side by side here. Series has one path, parallel has multiple paths. In a series circuit, the current measures the same everywhere, but in a parallel circuit, the current actually splits among the branches. In a parallel circuit, the voltage remains constant everywhere, whereas in a series, the voltage drops at each resistor. Can be calculated, and I showed you yesterday on how to add those together and make sure that they equal the battery's voltage. So please revisit that if you need to. Adding resistors in a series circuit decreases the overall current because, as you add resistors, RT is just adding them together. The bulbs dim as a result, and battery use decreases. In a parallel, adding resistors adds to the drawn current. It's the weird thing about it, right? Adding resistors decreases overall resistance in parallel, making your bulbs burn brighter. Again, that's a problem in the sense that you can overload the circuit, or your battery would just burn out really fast. So know these key differences. I am going to post a second 5-minute clip from kind of an old school teacher that I really like. He's a good artist too. I want you to view his additional examples. This is actually going to be required for you to move on to take your quiz tomorrow. So after you've watched that clip, that is all you have to do today. You certainly can work ahead on the quiz if you want to, if you have the time, but we're going to just still try to give you manageable amount of work each day. So it's up to you if you want to work ahead. Okay, so that clip will be where you found this lesson in Schoology, and that's all I have for you today. Thanks for watching.